So welcome back, and let's move on to the second speaker, Ozcan Zulger. So Ozcan, if you're ready, I give you the floor for your presentation.
Okay, I'm ready, Martina.
Okay, good morning.
Okay, can I start?
Yes.
Okay, thank you, Martina. I'm very pleased to join your workshop today as a speaker. And let me share my screen. Okay, is there any problem?
Now we can see your screen correctly. Thank you.
Okay. Okay. Hello, everyone. My name is Ozcan Zulger. I'm the visiting assistant professor at the Department of Computer Engineering in Middle East Technical University. I'm also a visiting assistant professor at the Department of Computer Engineering in Artificial University. Today, how can I close the Okay, do you see anything at the top of the page? I'm so sorry. No. Sorry, here. How can I hide the menu bar at the top of the page?
Yeah.
I'm trying to hide the menu bar here. Okay, okay, no, it's not this one. This one, okay. Sorry. I'm so sorry. I couldn't find. Okay. Today, the name of my presentation is the performance optimization and the efficiency of GPU. Okay, I'm sorry. I will stop and start sharing again. Just I'm so sorry. Okay, the contents of my presentation is the closest access to the global memory of the GPU, and the second issue is the device occupancy and the efficient utilization of streaming multiprocessors. And at the end, I will give brief information about the divergence problem of the work. Before starting my presentation, I'd like to show the boards I used in the experiment. I used Tesla K40 board, and its architecture is Kepler architecture, and there are some specifications about this board, important specifications. One of them is the number of streaming multiprocessor in the Tesla K40 board. It is 15, and the segment size of the global memory is 128 bytes. And the maximum thread that can be active at the time in a multiprocessor is 2048. I will also mention that. And the maximum thread that can be created in a block is 1024. And the maximum blocks that can be active in a streaming multiprocessor is 16. And the number of threads in a verb is 32. These are important parameters of the board. The reading from or writing to global memory on CUDA performs segment by segment, and the threads in a verb are physically related to each other. We know that 32 threads are resides in a verb. So this physically related means a verb completes its instruction when all the threads in the verb complete that instruction. And in global memory operations, if the threads in the verb access to the different segments of the global memory, the operations become serial. Here is the picture of non-coalesced access of the global memory. Here there are verbs here. The arrows are the threads in this picture, and the threads in a verb access to the different segments of the global memory, as you see. So the operations become serial. So how can we overcome this problem? The idea is to force the thread in the same verb access to the same memory, same segments on the global memory. This is the idea. Let me show you an example. Okay. Okay, here, and there's an example about memory coalesced access. We have two kernels here, which starts as global keyboard at the top of the page. You can say the first one is the full coalesced access kernel. The name of the kernel is full coalesced access, as you see. And the second kernel, the name of the second kernel is non-coalesced access. In the first kernel, in both kernels, there's a vector addition, and inside the for loop, a vector addition performs at each iteration of the for loop. In full coalesced access, the threads in the verb access to the same segment. Here, the parameter, the variable TID means the global thread ID. We calculate it by using the built-in variables of the kernel, and we get the global thread ID. The global thread ID are between 0 and the total number of threads minus 1. Okay. And by calculating this global thread ID, we are trying to access to the memory location of A and B. And as we see that the consecutive threads access to the consecutive memory locations of the global memory. So the verb, the threads in the verb access to the same segment. So the verb performs this operation in exactly one transaction, one global memory transaction. In the second kernel, here we generate a random number between 0 and the data size minus 1, or the number of threads, total number of threads minus 1. And the threads in the verb access to the that random memory location. Here inside the for loop, we generate a random number. Each thread performs this operation independently each other. Each thread pick a random number and access to that memory location here for A, reading A, and reading all the threads in the verb at access to the different segments of the global memory. A verb can perform this loading operation in at most 32 transactions. This is the example, and these are the other instructions. I cannot show all of the instructions because of the limitation of the layout. So I left the important ones here. and we call here the kernels. Let me show you the output. And we use CUDA event record in order to measure the kernel execution times. Okay. Okay, let me show you the results here in the first run. Before showing the outputs, I would like to give brief information about the metrics that I use in this example. I used the NV profiler of CUDA, and there are some metrics about the global load operations of the works. Here, the first metric is the GLD transactions metric. It gives us the number of global memory load transactions. This metric gives us the total number of global memory load transactions in that run. And the second metric, which is GLD transactions per request metric, it gives us the average number of global memory load transactions performed for each global memory load. I will show you what it means. So it is the average number of global memory load transactions performed for each global memory load. Let me show you the output. Now here in this example, the data size is 2/15, and we execute our program and get this execution times here. And as you see that the full coalesce access has 14.91x speed up over non-coalesce access. It is important. Let me tell you the outputs of the metric. For the full coalesce access, as you see that the total number of load transactions is 204,800, as you see how it is calculated. Since we have here, we have 1024 work, because the data size is now 2/15, and we create a thread for each data. So we have totally 2/15 threads in this example, and because of that, we have 1024 works in this example. So 1024 works read A in one transaction, read B in one transaction. So each work reads A and B in two transactions. So at each iteration of for loop, 2048 load operations performed, and since the number of iteration is 100 of for loop, we achieve 204,800 global load transaction in total. And the average is, as you see, that it is 1, because the verbs perform these operations in at most 1 transaction. So the average is 1. For the non-coalesce access, as you see that the average of the global load transactions are 30.63, as you see. So that so we can ensure that the verbs perform the operation in at most 32 transactions. It cannot exceed 32. For the second run, we set the number of data size is 2/22. Hence, the total number of threads is also 2/22. And as you see that the execution time of full coalesce access is here 0.009, and the execution time of non-coalesce access is 0.51. So the speed up of full coalesce access over the non-coalesce access is 52.22x. So it is also an important output, important result for us. When we check the results of the metrics, the total number of global load transactions for the full coalesce access is here 100 times 261,144, and the average of the global load transactions is exactly one again for full coalesce access, and for the non-coalesce access, the average global load transaction is 31.09. So that is also an expected result for us. So how can we remove or eliminate the non-coalesce access of the global memory? One of the approach is grouping. This approach is an approach that we did this approach is an approach that we used in our study in the past. Here, this is the reference. So what we mean by defining grouping? A group here consists of contiguous real segments. So this is important. The second characteristic is the number of segments in the group can be between 1 and data size divided by 32. 32 is the number of data in a segment here. So the smallest group consists of one segment, and the largest group consists of full segments in the global memory. By defining the size of the group, we can adjust the non-coalesce access as we wish. So how can we adjust it here? Our main target is to force the thread in the warp access to the same group here. Now not the same segment. Now we force the threads in the warp to access to the same group. Okay, let me show you now this new kernel. That kernel is about grouping. We call it as semi-coalesce access. And in this approach, we select a group before the for loop. We select a random group, and inside the for loop, we load the data within this group in a random way. So we generate a random numbers and read the data within this group, within the selected group, at each iteration of the for loop. And we set the number of segments of the group to 16. Okay, that means the group consists of 16 contiguous real segments. So the memory operations of a warp will perform at most 16 transactions. In this example, the operations perform at most 16 transactions. Let me show you the output. Okay, in the first run, we set the data size to over 15. So that the total number of threads is also 2 over 15. And we have 1024 warps in this example. When comparing the execution time we achieve 6.96x speedup over semi-coalesced access, and we achieve 14.86 speedup over non-coalesced access. And when we examine the result of the matrix, the result of full coalesced access and the non-coalesced access are similar to the previous example. And the result of semi-coalesced access is 13.41 for the global load transaction per request metric, as you see. So we know that it can be at most 16 transactions. So we can be sure that our implementation is also true and the result is the expected one. And it cannot exist 16. And in the second run, the data size now is 2 over 22. So the total number of threads is also 2 over 22. And with full coalesced access, we achieve 22.22x speed up over semi-coalesced access and 51.86x speed up over non-coalesced access. And again, the results of full coalesced access and the non-coalesced access in the matrix are similar to the previous experiment. And for the semi-coalesced access, the global load transaction per request is, or the average is 13.41. It is also an expected result for us. Okay. It is occupancy. Occupancy is the ratio of active verbs to the maximum number of resident verbs supported on a multiprocessor. And the occupancy is related with limitations of the streaming multiprocessors. These limitations are the maximum number of threads per multiprocessor. It is 2048. That means at most 2048 threads can be active in a stream multiprocessor. And the second limitation is the maximum number of threads per block. That means 1024 threads can be created in a block. And the third limitation is the maximum number of blocks per multiprocessor. So that means 16 blocks can be active in a multiprocessor. And the third one is about the shared memory and the registers. We can check the use of shared memory and register by using this flag while compiling your application. And the main target of the occupancy is to find the optimum number of threads in a block in order to achieve maximum occupancy. This is the main target. Our target is to find the optimum number of threads in a block to achieve maximum occupancy. So let me show you some examples about it. If you set the number of threads in a block to 64, at most 1024 threads can be active in a streaming multiprocessor. Why? Because of the limitations of the board, at most 16 blocks can be active. Since the number of threads in a block is 64, at most 1024 threads can be active. But we know that 2048 threads can be active in a multi-stream multiprocessor. So we achieve 50% theoretical occupancy. In the second one, when we set the number of threads in a block to 128, at most 2048 threads can be active in a streaming multiprocessor. Because at most 16 blocks can be active, and 128 threads are created in a block. So at most 2048 threads can be active in this scenario. And so we achieve 100% theoretical occupancy. And in the third example, if you set the number of threads in a block to 1024, so at most 2048 threads can be active in a streaming multiprocessor, and we achieve 100% theoretical occupancy again. But in this one, only 2 blocks can be active because of the limitation, but it is not important for the theoretical occupancy. So again, we achieve 100% theoretical occupancy. Okay, now let me show you an example. And again, I define the kernel. Started with global keyboard. And again, a for loop here. And inside the for loop, there is a if-else structure. And at each condition, a vector addition or vector subtraction or multiplication or division will perform. The iteration of for loop is very huge because I'm trying to force the execution time of if-else structure dominates the total execution time. And there is no warp divergence here. I will mention briefly, but here in this if-else structure, there is no divergence. I define 2 scenarios here. In this example, in the first scenario, they are related to the number of threads per block, by the way. And in the first scenario, we set the number of threads to data size until data size becomes 2/11 here. In the first scenario, we set the number of threads per block to data size. Data size are between 2/15 and 2/22. So we set it to data size. And in the second scenario, we set the number of threads to 32 until data size is 2/10. Then we double the number of threads per block as the number of data doubles here until the data size becomes 2/15. Here it is the summary of the scenario in a table. Let me show you again here. The data size starting from 32 up to 2/16. Okay. And in the first scenario, we set the number of threads per block to data size until data size becomes 2/11. And we fix the number of threads to 1024 because of the limitation. And in this scenario, as you see that at first one block is created until the data size is 2/11. One block is created. And the number of blocks doubles as the data size doubles. Here. Okay, this one. So when we check the theoretical occupancy here, we achieve 100% theoretical occupancy when the data size is 2/7. Why? Because we increase the number of threads per block, because the theoretical occupancy is related to the number of threads in the block. So we achieve 100% when the data size is 2/7. For the second scenario here, we set the number of threads to 32 until the data size is 2/10. Then we doubles the number of threads as the data size doubles until the data size is 2/15. And we fix the number of threads to 1024 because of the limitation. And as we check the number of blocks that created in the scenario here, it starts with 1 block and the number of blocks doubles as the data size doubles here. It is different than the first scenario. And the theoretical occupancy is very low until the data size is 2/11. Why? Because we do not increase the number of threads for the small number of data size. So we achieve theoretical occupancy for the second scenario. We achieve 100% theoretical occupancy when the data size is 2/11 here. So with the first scenario, we try to increase the theoretical occupancy. With the second scenario, we try to create more blocks and we try to distribute these blocks to the streaming multiprocessors evenly to utilize the streaming multiprocessors efficiently. So our target is to obtain efficient utilization of the streaming multiprocessors. As you see that in the first scenario, here, when the data size is very low, only one streaming multiprocessor is active, the remaining ones are idle. I will show you effect of these issues. Before showing the outputs of the experiments, I would like to give an information about the metrics that I used in the experiments. The first metric is related to the efficient utilization of streaming multiprocessor. The definition is that the SM efficiency is the percentage of time at least one work is active on a multiprocessor, average over all multiprocessors on the GPU. That means, first, the ratios of the running time of each streaming multiprocessor to the total running time of the application is calculated. We calculate the ratios of running time of each streaming multiprocessor to the total running time of the application. And by getting the average of these results, we achieve the result of this metric. The second metric is achieved occupancy metric. It is the ratio of the average active works per active cycle to the maximum number of works supported on a multiprocessor. So it is related to the average active works per active cycle. And achieved occupancy cannot exceed the theoretical occupancy. Okay, let me show you the result of the experiments. We have already examined these parameters, and there are here results of SM efficiency and achieved occupancy and execution time. So the values with yellow one, with yellow background, means both scenarios have the same values of parameter. So the outputs of the metrics are almost same because all of the parameters are same. The values of all of the parameters are same. For the green ones, the result with green background means that scenario is better than the other scenario for that metric here. So let's look at the some efficiency metric. Second scenario is better than first one, where the data size is between 2/6 and 2/13 here. For the theoretical occupancy, first scenario is better than the second one, where the data size is between 2/6 and 2/10. And for the sheet occupancy metric, the first scenario is better than the second one, where the data size is between 2/6 and 2/13. So they are expected results for us, as I told you before, because we try to distribute the blocks evenly to the streaming multiprocessors for the second scenario, and we try to increase the theoretical occupancy for the first scenario. But when we check the execution times, the execution time of second scenario are better than the first one for the data size between 2/9 and 2/13, as you see that. So the execution time of the second one is better than the first one. So that means here, when we check the results, that means having better theoretical and sheet occupancy does not always mean better execution time performance, as we see here. In this application, the SM efficiency is more effective on the execution time of the kernel. Although S1 has better occupancy, the execution times of S2 are better than those in S1 in some of the cases. So in this example, not that the better theoretical occupancy is effective on the result. Utilization of the streaming multiprocessors is more effective on the execution time of the kernel. And another issue here, as you see that the sheet occupancy, is lower than theoretical occupancy. It cannot. We know that a sheet occupancy cannot exceed the theoretical occupancy, but here it is lower than the theoretical occupancy. The regions are here. The regions are. The regions can be unbalanced workload within blocks, or can be an unbalanced workload across blocks, or too few blocks large, or partial loss rate. You can check the you can obtain the detailed information about these regions within this website. And the last issue I would like to tell you is work divergence. This is the last issue. Some of the structures, such as if-else structure, are considered as a single instruction for a work. So that means a work completes if-else instruction when all the threads in the work complete if-else instruction. If the threads in a work execute the different paths of if-else structure, executing these paths becomes serial. Let me show you an example here. TID is the global thread ID, and we perform a modular operation here over the global thread ID. So in this example, At first, the threads with even thread ID in the work execute the if path, and the remaining threads are idle. Then the threads with odd global thread ID execute the else path, and then the remaining threads are idle. So the operations become serial. How we can overcome this problem? One of the approach is using work ID rather than global thread ID in the condition of the if structure. Here, rather than using global thread ID, we use work thread ID. By dividing the global thread ID to 32, 32 means the number of threads in the work. So we obtain work ID. So in this scenario, the threads whose work ID is even execute the if path. The threads whose work ID is even execute the if path. The threads whose work ID is odd execute the else path. So executing the paths of the work does not become serial with this approach. And I would like to show you an example. This is the last example. Here, I define two kernels. The first one is about the no divergent versions of the if-else structure. Here, there is no divergence because we use work ID. And in the second one, there is a work divergence because we use global thread ID. And in the first one, first form execute addition. Here, the second form execute subtraction, third one multiplication, and so on. In the second one, first thread in the verb execute addition, second thread in the verb execute subtraction, and so on. And again, we use for loop in order to dominate the total execution time for if-else structure. And the memory operations are coalesced. There is no non-coalesced access. So the work divergence can dominate the execution time. Okay. Let me show you the result. Before that, I would like to tell you the metric that I used. It is verb execution efficiency metric. And it gives us the ratio of the average active threads per verb to the maximum number of threads per verb supported on a multiprocessor expressed as percentage. So we will obtain result with percentage. Here, the number of data size is 222 again. And the execution times here, the no divergent versions achieves 3.1 speed up over verb divergence kernel. We achieve 3.1 times speed up. When we check the result of the metric, for the divergent case, we obtain 34% in average. And for the no divergence case, we achieve 100% because there is no divergence here. All of the threads execute the same path. But in the divergent case, it is not. Because of that, we achieve 3.1 speed up. And these are the references that I use in this presentation. And thank you so much for your attendance and listening me.
And thank you so much for your interesting presentation, Ozcan. And I've taken up your request to create a GitHub repository to collect all the example proposed today. And I will let you know shortly if it is possible or not. So